Hello, everybody. Welcome to Chapter 9 lectures. They're going to be pretty short. I think it's actually just going to be one clip, maybe a little bit longer than typical short individual clips. So I'm going to talk about the Lewis structures and the molecular geometries that result from the Lewis structures. And the geometries are determined based on the VSEPR, which stands for valence shell electron pair repulsion. So it depends upon how the electron pairs repel each other, what geometry will result. And so this chart that you see here might look a little overwhelming, but I'm pointing it out to you first so that when you're preparing for the final exam or when you're taking the final exam, that you have a copy of this chart close by, because it will help you to answer questions related to all of these different characteristics of Lewis structures and molecular geometry. And I posted a copy of these charts that I created in the Blackboard content folder. So you could maybe want to print those out or just have a tab open for them when you're taking the exam. Okay, so I'm going to go on to kind of just give you a quick intro, then I'll come back to this chart. So I'm going to go through the development of all of the characteristics of the chart based on one example first, then we'll go back to the chart. So let's say we have carbon tetrachloride, which is CCl4. And we learned last chapter 8 how to draw Lewis structures. So all of those features of Lewis structures carry over to this chapter. So the first thing you do when you're drawing a Lewis structure is you count the number of valence electrons. So this molecule has 32 valence electrons. So then as we learn, the first thing you do is you put the least electronegative element at the center, or the one that's singular, or the fewer number is kind of how I always look at it. And then I distribute my terminal atoms, and I would connect each terminal atom with a dashed line, and we know that the dash represents 2 electrons each. And then I would distribute each of the remaining electrons, 6 remaining to each of the chlorides. So that one's pretty straightforward. So then the molecular geometry that results from this, Mg, molecular geometry, I'm abbreviating here, is called a tetrahedron. And the electron geometry is also a tetrahedron. Now, the electron geometry has to do with the number of electron pairs that surround that central atom. And it's really only the central atom, or in some cases, there's multiple central atoms, because if you had a C2 here, you would have more than one central atom. But we're going to stick with single central atoms. So you describe your molecular geometry and electron geometry around your central atom. And when you have a tetrahedron, you have a specific bond angle. And the bond angle here for the tetrahedron is 109.5 degrees, but some resources just call it 109 degrees. So then another notation that we often use to kind of generalize this is we call it the AX notation. And the AX notation just means that I represent the central atom with an A, and then I represent the terminal atoms with an X, and then identify how many terminal atoms that I have. So there's my A, the carbon, and then my chlorines would be my X's, and I have 4 of them. And then we talk about what's called the hybridization, and that's what the orbitals of the valence shell will do in order to create the characteristic number of bonding sites for that element. So, for example, I'll talk about carbon's hybridization ability. And every atom in the molecule can hybridize, but typically we're only interested in how the central atom can hybridize in order to bond. So the carbon, we know that the ground state orbital diagram for carbon for the valence shell only. It would also have a 1s2 orbital, but we're not including that because we're only interested in the valence shell for bonding. So I would have 2 electrons in the 2s orbital, and then I would have 1 in each of 2 of the p orbitals. A bond occurs where there's a half-filled orbital. So since we know that carbon absolutely can form 4 bonds, and most can, there are certainly exceptions to this octet rule that we'll talk about. So what carbon does is that it bumps one of the 2s electrons out to a 2p orbital. And so now I have created 4 half-filled bond sites where something, so what happens is that when the chlorine comes along to bond, it's going to put 1 electron there, 1 electron there, 1 electron there, and 1 there. And it's those 2 electrons in each of those orbitals that create these bonds here. Okay, and so we say that they are sharing those electrons. So we have to be able to call this hybridization, identify what this hybridization is. And so to identify it, I'm going to say, all right, I have 1 spot for bonding in an s orbital. So that's really an assumed 1 there. We don't have to put the 1 in, but there's an assumed 1 above the s. And then I have 3 spots in p orbitals where bonding occurs. So I call this sp3 hybridization. So my carbon does sp3 hybridization. And hybridization, as you saw in one of the videos that I posted on YouTube, that the hybridization can also occur for these terminal atoms. But what we know is that this single bond occupies a hybrid orbital, and unshared pairs also occupy a hybrid orbital. So if I had to identify the hybridization of this terminal atom chlorine, it too would be an sp3, meaning that there's 4 places for bonding to occur. But I wouldn't worry too much about that. We're not going to talk about the hybridization of the terminals. I won't test you on that. Okay, so then we're also interested in whether or not the molecule is polar or nonpolar, not the bond. We talked about polar versus nonpolar bonds in chapter 8, but now we're talking about the whole molecule. And the way you look at this is if the molecule is symmetrical, I forgot a C there, is symmetrical, then it's considered nonpolar. All right, so it's really all about, is it symmetrical or is it not symmetrical? And if it is symmetrical, then it's considered a nonpolar molecule. It just means that everything is distributed evenly around it. And I always say, if you just look at it, you should be able to tell if it's symmetrical or not. And that's, really the best we can do without building them. But the simulation that you're going to do will definitely let you see the molecules in more dimensions and be able to then be able to distinguish what symmetry is versus non-symmetry and give you a better idea of where the bond angle value comes from. So those are, anything that's a tetrahedron is always going to be a 109. All right, so now let's go back to the table, and I'm going to show you how to interpret the table. So I've given you some examples here. This first one is what I just did. Well, I did CCl4, but CCl4 is going to look in terms of geometric structure, just like CCl4. So then the next one, I know we did this molecule last chapter, and we, here's, be careful that H is not attached to that N. So when we have one unshared pair, it's going to be called a trigonal pyramidal. And that's because this unshared pair of electrons will cause this valence shell electron pair repulsion and force this molecule away from the tetrahedral structure. So when I look at the electron geometry of this molecule, it's going to be the same as the electron geometry for the tetrahedron. So although its molecular geometry is called a trigonal pyramidal, the electron geometry is a tetrahedron because we look at 1, 2, 3, 4 bond sites. So the electron geometry is all about the number of bond sites. Whether or not a bond is attached, it doesn't matter. You still call it the tetrahedron for electron geometry. But molecularly, it's different. The bond angles are a little bit smaller, and the AX notation, now we identify the central. The N would be the A. The H would be the X3, or the 3 H's would be the X3. And then this E1 means that there's one unshared pair of electrons. So that is right there. That's what that E1 represents. And now the hybridization is still the sp3. Now this is considered polar because it is not symmetrical. That unshared pair of electrons makes it unsymmetrical, therefore polar. So then the next example, we did this Lewis structure last week. Its molecular geometry is called bent, but because it now has 2 unshared pairs and 2 bonds, it still has 4 bond sites. It doesn't use 2 of those sites, but therefore its electron geometry is still a tetrahedron. But the VSEPR, the valence shell electron pair repulsion, causes the bond angles to be even a little bit smaller. And we call that AX notation A. X2, A is for the oxygen, X2 is for the hydrogens, and then the E2 is for the 2 unshared pairs of electrons around the oxygen. Okay, and still, since I still have all of those bond sites, my hybridization is sp3, and now these unshared pairs make it really very polar. And so now I go through and I develop, we did many of these molecules in our last chapter, but here are the names for each of those molecules. Here are the electron geometries for each of those molecules and bond angles, and then your AX notations, okay, which, this one I made a mistake on. This is an AX2, but this one is an A. One oxygen is the central, A. There's my 2 X's, but that should have an E1 because it has 1 unshared pair of electrons. So the nice thing about all of this is that we can more or less ignore a double bond when we're identifying geometry and bond angles and hybridization. So it's really just part of your Lewis structure or your resonance or for determining formal charge, as we learned in last chapter, but you don't have to consider it when you're doing molecular and electron geometry. So that's all of those molecules. And then the next would be some of the expanded octets. And we talked about those, and there's some videos on expanded octets. And so I went through and identified all of the molecular geometries. And then the same principle applies for the electron geometries. The bond angles get a bit more complex, but of course you don't have to memorize anything here because you'll be able to have these charts available to you. And then the hybridization here is a little bit different. all you have to do to identify hybridization is to say, okay, how many bond sites do I need? Well, this has 5 bond sites. So then I have to have this sp3d. So what I have is I have one of an electron in an s orbital. I have 3 p's with 1 electron each, and I have 1 d with 1 electron each. That would leave me with 5 total bond sites, and that's what I would need. And then the same thing here, although I only have 4 terminal atoms, I still need a bond site for that unshared pair, so it becomes sp3d again. And so all of these are sp3ds. And then the polarity is based on, again, the symmetry of the molecule. How the only word is symmetrical. How much is everything spread equally around the molecule? And so the first one's nonpolar, the last one's nonpolar. Even though there's these unshared pairs, everything is spread out equally. And some of these you can see nicely in the tables in your textbook that show them in 2-dimension, which is a lot more clear in terms of trying to identify the symmetry of the molecule. And then the last slide here are 6 electron pair molecules. These were 5 electron pairs. These are, what we call the expanded octets that we talked about a little bit last chapter. And these are more expanded octets. These are all based on the octahedral shape. And so I go through and I show you the Lewis structure, identify molecular and electron geometry. This one is an AX6 notation. And now the hybridization, now I need to show 6 spots, 1 for the S, 3 for the P, 2 for the D. So that would open up 6 spots for bonding. And then everything holds true here, where now I only have 5 terminal atoms, but I still need a spot, a bonding spot for that unshared pair. So my each of these all have the sp3d2 bonding. And so you can see with this molecule here, this molecule here, that the AX notation, there's your one central X, E, your xenon, then there's 4 fluorines, and then there's 2 unshared pairs of electrons. And then the only other thing that I wanted to talk about would be something that is mentioned in one of the videos, and you should definitely watch it. It's one of the Brightstorm videos, and it's one that talks about hybridization. It's very good because it talks a little bit about the difference between the first bond in a double bond and the second bond in a double bond. And they have different names and different characteristics. The first bond of a multiple bond is called a sigma bond. And the second bond of a multiple bond is always called a pi bond. And what's important to note here is that sigma bonds hybridize. So, and pi bonds do not. Pi bonds form in a different manner. All right, it's an overlap of orbitals, while sigma bonds are the ones that hybridize. So that's why when we're identifying our hybridization, we don't worry about the second bond in a multiple bond. So I think I'm going to stop there and let you guys kind of work through some of the problems, which I think would be very important to go through. I know that you don't have to turn them in for grading, but they'll be very helpful to help you, kind of gather a little bit better understanding of this material. I think the videos I posted in the YouTube videos are excellent, and I titled each one. So if there's some segment that you're not quite comfortable with, you could, just go and watch that one video. They're all very short. I don't think it'll take you a lot of time. And then again, the simulation that you have to do this week, the lab simulation, and I said I would count it as a homework assignment. Very, very important um, to work through that, because I think it will give you a very good understanding of this material. Please check in with me anytime this week. We'll make time for you, either virtually or through email, whatever works best for you. So have a nice week.